Hi, good evening.
Hi. Let's just wait for a couple of minutes in case Ada wants to join, and then we can start. Okay.
Sure, sure.
Yeah.
So I could not see lecture videos because I was absent in last 2 weeks
Okay.
discussion, and I could not see lecture videos of the week uh, 7 and then 8.
Okay.
So uh, would I be able to understand today's discussion? Number one. And if I continue seeing videos from the week 9 onwards, then would I be able to, by skipping the videos of the
Okay.
week 7 and 8, would I be able to understand the remaining content of this course?
So, was BPP covered in week six, or were randomized classes started in weeks six
Which
or in
one?
seven? Randomized complexity classes like BPP, RP,
Okay.
ORP.
Yes, so it was started in week 6.
Okay, then I think you should be able to follow at least some of today's session. And what is covered in week nine?
So week 9 is about this is a search bipartite perfect matching in RNC, problems and the Valiant Vajirani's theorem, and then this hash p. So yeah,
Okay.
counting complexity. So would I be able to understand this stuff by skipping? Because I'm really running short of time, so I'm not sure whether I would be able to. Uh, I could spare that much time to view the lecture videos of the 7 and 8 and
So
8 10 hours.
okay, let me do one thing. Let me open the exact syllabus and see.
Yeah.
Yeah. Oh, so you missed most of circuit complexity, right?
Yes. So
So
yeah.
I don't think there would be too much circuit complexity in the coming weeks. So I think you still might be able to follow.
Okay, that's very
Yeah.
good. And even in the week number 7 and 8, can you tell me the minimal requirement in case if circuit complexity is required, the
Okay.
minimum,
Yeah.
yeah, which I can refer.
Okay. So what you can do is you can uh, read what's okay. So I would suggest that you look at the lecture notes first instead of the videos,
Yeah.
and look at what circuits are. Uh, the class P slash POE, the class AC, and the class NC. I think this is the minimal requirement. Yeah,
Okay. Okay.
yeah,
Fantastic. Yeah. Thanks for your advice.
yeah,
So I'll do it today's evening itself. Yeah.
yeah. Okay, so it's already 6:05, so let's start. Yeah. So yeah, today we'll first solve last year's week eight assignment. Then what we'll do is we'll solve this year's week eight practice assignment, and then if we still have time, we'll solve this year's week seven assignment. And so, like, there might be some things that there might be some classes or terms that you are not aware of because you skipped those two weeks. So, in that case, like, just after I finish reading the question, just ask me what those are. Okay.
Fine.
Yeah. Okay. Okay. So, my screen is visible, right?
Yes. Yes. Visible.
Yeah. Oh, okay. Great. Okay. Yeah. So, the first question is all languages in BPP can be represented by a polynomial size circuit family. Is this true or false? So, should I define what polynomial circuit families are?
Yes. Yes. I know what
Okay.
BPP is, and I do not know this polynomial size circuit family.
Okay. So, do you know what a Boolean circuit is?
Yes, yes,
Okay. Yeah. So, a circuit is, takes n inputs and has one output, right?
yes.
So, it naturally computes a Boolean function on n variables. Okay.
Mm-hmm.
Now, what you can do is you can take a language and just focus your attention on strings of length n, right?
Mm-hmm.
So when you do that, the language becomes a Boolean function, right? Because if x is in the language, you define f of x to be 1. When x is not in the language, you define f of x to be 0, right?
Yes.
So basically, what you can do is the following. You can compute a language using circuits as follows. For every n, you get a function fn from the language, right?
For every n, and what is n here?
N is the number of, so n is the size of the input string.
Okay.
Yeah. So for every n, you get a
Okay.
Boolean function. From the language, you get a Boolean function, fn, right?
Yes.
And that you can compute using a circuit Cn.
Okay.
So for different n's, you have different Boolean functions computed by different circuits, right?
Yes.
And this entire set of Cn's is a sequence, right? C1, C2, C3, and so on. That is called a circuit family.
So how this? I mean, how? So are we mapping a string to a circuitry, or what? Are we mapping a? I mean, how are we mapping a language in general to a Boolean circuitry? I mean,
Okay,
to a
so
circuitry.
a language maps to a Boolean function, right? So for
How?
example, consider the language. Uh, consider the language halt. Okay,
Okay.
and fix some n. Let's say n is equal to 1000.
Mm-hmm.
And what we are going to do, okay, what we want to know is, given a string x of length 1000, does x in halt or not? Okay,
Okay. Yeah.
so this we can convert into a function as follows. Define a function f so that fx equals to 1 if and only if x is in halt.
Yes.
So now if you can compute this function, then you have solved the halting problem for strings of length 1000, right?
Yes.
Okay, so this is how you convert a language to a Boolean function.
But the value of n could be pretty large, though
Right.
it cannot be infinite, but it could be pretty large.
Right. So what you do is you convert a language to a family of functions. So so you start from zero. For strings of length zero, you have function f0. String of length one, you have function f1. String of length two, you have function f2, and so on. Right. So you have a sequence of Boolean functions f0, f1, f2 corresponding to the language.
Yes.
Okay, and fn decides the language, decides whether strings of length n are in the language or not. Right.
Yes.
And then what you do is you compute fn using a circuit Cn. That you can do, right? Because fn is a Boolean function.
Right.
So this is how you map language to first a family of Boolean functions and then to a family of circuits.
Yes. 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 Fine. Fine.
Okay. So this sequence
So
of circuits C0, C1, C2 would be called a circuit family.
yes, and now this mapping of the Boolean functions to the circuitry is not clear. Say if I'm mapping a Boolean function
Hmm.
which is taking say n number of the inputs, then how am I constructing a
Okay,
circuitry?
again, so one way to do it is just write the Boolean function in its CNF or DNF form
Mm-hmm.
and then use a small CNF or DNF, right? For example, uh, if the XOR function is this, right? Uh, x1, x2 complement or x2, x1 complement, right? This is the XOR function.
Yes.
So what you can do is here's a circuit. It takes the topmost gate is an OR gate. That OR gate takes two inputs, both are AND gates, and the first AND computes this, like the second AND computes this.
Yes.
So by just writing every Boolean function in its as its min terms or max terms, you can do it.
Yes. Yes.
But this is just one way to do it. There can be some very efficient circuits to do it as well, right?
Mm-hmm.
Yeah.
Mm-hmm. Yes.
And yeah, so that's a circuit family. And a circuit family is polynomial sized if Cn has size poly n.
So can you write this term here on the board? What did you say? Because your voice
Oh,
somehow is, yeah.
okay. So the circuit family Cn is poly-sized if size of Cn, which is equal to the number of gates in it,
Mhm.
this.
Oh, I see. So
Yeah,
if the number of the operations in the Boolean expression are polynomial in
in the
number,
Boolean circuit.
yes, so then there would be polynomial number of the gates, and that will result into the polynomial size of the circuitry.
Yeah,
Okay, okay.
yeah. And as far as this question is concerned, so what we know is, okay, this I will. Okay, so this is true, and the reason is this. So it's known that BPP is in P slash poly, and P slash poly is the class of all languages computed by poly-size circuits. Yeah, so this is known, and since P slash poly is just the class of all languages that are computed by poly-size circuits, the statement is true.
Okay.
Yeah, this is fine.
Yes.
Okay, so let's look at the next problem. The problem is, suppose a bipartite graph G does not have a perfect matching, then the permanent of the adjacency matrix of zero if of G is what? So yeah, the permanent is just this. Permanent of a matrix A is sum over all permutations. So I'm assuming that G, okay, let me assume that G is n variant. Okay, so I'm assuming that G has n, so G is a bipartite graph, right? So in both its left and right vertex set, it has n vertices. So its adjacency matrix or its bi-adjacency matrix is going to be an n cross n matrix.
Okay.
Yeah, and the permanent of a matrix is just this. Yeah, this is the permanent. Okay, and so the question is, if there is no perfect matching, then uh, what's the value of the permanent of this matrix? So what would be your guess?
So I mean, what this permanent of the matrix indicate? Like say this is symmetry matrix, or what this Sn here? I mean,
So
what is it?
Sn, okay, okay. Sn is the set of all permutations of 1 to n.
Okay, okay,
Yeah.
symmetry matrix kind of the thing.
So, okay, Sn is not a symmetric matrix, right? Sn is, so every element in Sn would map 1 to n to 1 to n. It's a 1
Yes,
1 onto function from 1 to n to 1 to n, right?
yes. So
Yeah,
sigma is a permutation here,
right.
and then this what this pi I is the element of n indicates. So what this a I and
So
then
this is a
sigma.
product.
Okay, the product of what?
These.
So product of this a I sigma I. So what this a I sigma I then refers to?
AI sigma is just the I comma sigma as entry of A. A is a matrix, right?
I see.
Yeah. Okay, so so the answer is zero. And so instead of just proving this, I'll prove a more general claim, and it's this. So in that claim is one interpretation of of the permanent, and the claim is, so let G be a bipartite graph. Okay, let be a bifurcated graph such that uh, size of L equals to size of R. That is the size of both the left vertex set and the right vertex set is N, and A be the adjacency matrix of G. Then the number of, okay, so I'm going to use hash for number of perfect matchings in the graph is the same as the permanent of. Okay, so let's do this. Okay, so to prove this, we can do, so we'll do the following. We'll first show that the permanent of A is at least the number of perfect matchings in G, and then that the number of perfect matchings in G is at least the permanent, and so the two have to be equal. Okay, so I've already defined the permanent, and okay, so ev- every perfect matching can be represented by a permutation on N, right? Because if L were if the vertex at L were L1 to Ln, then a perfect matching would map each Li to a unique Rj, right?
Yes.
Yeah. So every perfect matching can be thought of as a permutation. So let sigma in Sn be such that, okay, I first need to say L is this. L equals to L1 to Ln, and R equals to R1 to Rm. Let sigma in Sn be a permutation, right? Only, yeah, be such that this set Li R sigma I is a perfect matching. I in L.
So what this tuple here indicating? Li is getting mapped to what? Li is getting mapped to the R of this sigma. So what this sigma of I is the subscript
Okay,
mean?
okay, so I, okay, so what are the elements of R? The elements of R look like Rj for some number j in 1 to n, right?
Correct.
And sigma is a permutation that maps 1 to n to 1 to n. So sigma I itself is a number between 1 to n, right?
Yes. Yes.
So you can, so here I'm treating sigma as a function. So
Correct.
sigma is just whatever it maps I to,
Right. Right. Right.
right? And now, so since this is a perfect matching, it means that Li R sigma is an edge, right?
Yes.
So in the adjacency matrix, as for all I, Li comma R sigma I is an edge. AI sigma I is 1. Okay.
Right.
So product I in N, AI sigma is 1. Because each and every of the AI sigma is 1, right?
Yes.
So each perfect matching contributes 1 to the permute use. 1 to the permanent, right? Yeah, because for every sigma, you have this term in the permanent. So whenever you have a perfect matching, the term for the corresponding sigma would be 1, and the permanent would go up by 1, right? So
Mhm.
each perfect matching contributes 1 to the permanent, and so uh, permanent. So no, okay, so I can write this because in the permanent, first of all, the matrix is 0, 1. So each and every one of this is going to be 0, 1. And so each and every one of this product is going to be 0, 1, right? And there is, and there are, so there are no cancellations at all. So, so whenever a sigma contributes 1 to the permanent, that one is never cancelled out. That is why I can write this. So is this fine? Is this claim fine?
Yes, so number of the perfect matchings is equal to the permanent of A. How can this be greater than or equals to this thing?
Okay, right. So what can happen is, what if there is some sigma such that this is 1, but sigma is not a permutation? Sorry, sigma is not a perfect matching.
Mhm. Can
Okay,
you
in
can
fact, that cannot happen. That's the next part I'll show.
Okay, okay,
So,
fine,
okay, so
fine.
what right now what I showed was that a perfect matching contributes to a term which equals to 1 in the permanent. Next, what I'll show is every term that contributes 1 to the permanent corresponds to a perfect matching. So the number of perfect matches and permanent has to have to be the same, right?
Yes.
Yeah, so this was just the first part. So let me add a page. Yeah. Conversely, if for some sigma in Sn, uh, product I in N, Ki sigma I is 1, then for all I in N, Li comma R sigma I is an edge, right? Why? Because okay, so this product is 1. That means each and every element is 1. And this means that Li comma sigma I, R sigma is an edge because that's how an adjacency matrix is defined, right?
Yes.
Yeah. So, okay, and since sigma is a permutation, this means that is a perfect match, right? Yeah, so is this fine? Why is this a perfect match, right?
Yes.
Yeah, because so we are going over all n, and since sigma is a permutation, sigma I would be different. So every Li is being mapped to a unique and distinct R sigma I. And this is exactly how we define a perfect matching, right?
Yes.
Yeah, so uh, permanent of A is less than or equals to number of perfect matches.
Yeah, all right. So yeah.
Yeah,
Therefore the equality matters.
right. It turns out I did not need this page. Let me delete. Okay, so is this claim fine?
Yes,
Yeah. So now, given the claim, it's easy to answer the question, right? So there are no perfect matchings. So the permanent has to be zero.
it has to be zero.
Yeah.
Yes,
Yeah. So is this fine?
yes, yes.
Yeah. So then let's look at the next problem. So the next problem is consider the following adjacency matrix of a bipartite graph G. The number of perfect matches in the graph is what? So we can solve this using the previous claim, right?
Yes.
Yeah.
So the number of the perfect matching here is equal to uh, this. Uh, so
So,
yeah, instead of I can use the common sense also. So the value would
yeah,
be
that
two.
also works. Yeah. So what did you say? What's the number of perfect matches?
Two.
Okay, which two?
So like say see here. So let us focus on those entries. Okay, no, those entries are not here. So we'll have to skip the diagonal side entries, and then the remaining entries we can think of may form a perfect matching.
Wait, why are you skipping the diagonal entries?
Because what's the meaning of mapping? Say, like say here, three elements are getting mapped to three elements.
Oh, so your voice broke.
Three elements are getting mapped to three elements. So therefore, what could be
Right.
the meaning of say? So like what this entry here? One is mapping to. No, no, no. So yeah.
Okay,
Uh,
so let me write this on the. So this is L1, this is
yes.
L2, this is L3, this
Yes.
is R1, this is R2, this is R3. And an entry 1 over here means that L1 R1 is an edge. This entry means that L1 R3 is an edge. This means
Mhm.
that L2 R1 is an edge and so on, right?
Yes.
Okay, so now can you tell me how many perfect matches would be there? Or at least let's say start listing out some perfect matches.
Yes. So let us say L1 is getting mapped to R1
Yeah,
here, and then L2 is getting mapped to R2. Fine, and then L3
right.
to R3. So this is one matching, and the other could be that
Yeah.
L1 mapped to R3, and then L2 mapped to R2, and then yeah, so
L1 to, so okay, why
L1
did you
to
say L1 to?
L1 to R3,
Okay,
and then L2 to R2.
L2 to R2, but then you don't have anything for L3, right?
Yes. So yeah, so I'll have to, but then I do not have any other chance, any other because so the
So
other
you
one
can
could be
do
that I map
L2 R1, right?
L2 R1.
So
Yes.
this is gone, and you're still left with this.
Yes. Yes.
L3 R2,
The other one could be that. So these are the only top two possibilities. The L1 can map to one R1, or L1 can map to R3. Since
right?
L1 cannot map to any other thing, so third possibility will not arise.
Okay, but when L1 maps to R1, okay, so when this is taken, you have this matrix, right?
Hmm.
So instead of mapping L2 to R2 and L3 to R3, you can switch. So you can have this.
Right. L1 R1, and then yes.
So we are using this, and this.
Mhm.
And so these are the only three. Because, okay, as you said, you can either map L1 to R1 or L2 to L1 to R3, right? So let's
Mhm.
map L1 to R1. Then we are left with this matrix.
Mhm.
And oh, so this, okay, this is a 2 cross 2 graph. So you can have only like two perfect matches over here, right?
Mhm.
So we have taken care of both of them over here. So L1 R1 is done. Now we are only left with L1 R3, right?
Mhm.
So then we have this matrix. And over here, the only perfect matching is L2 mapping to R1 and L3 mapping to R2. This L3
Right.
can't map to R1. Yeah. So we only get these three perfect matches.
Yes.
Yeah. Okay, so is this fine?
Yes, yes.
Yeah. Okay, so the next question is,
Yes.
yeah, uh, how many distinct functions are there from 0, comma 1 to the n to fm? So fm is just this thing. And you do operations addition and multiplication mod m.
Okay, okay.
Yeah. So how many functions are there from 0, comma 1 to the n to fm? 2 to the mn, m2 to the n, m2 to the n, and n2 to n to the 2 to the n.
Okay, so how many functions are possible in general uh, from these values 0 to 1 raised to the power n? So how many
Right.
different functions are possible? So here we can have, say, how many different functions are possible. So uh,
Okay, so
I mean,
fix one string over here. For
mhm.
that string x, how many possibilities are there for fx?
So there are m number of the possibilities,
Right. And how many strings are there?
2 raised to the power n.
Right. So what does that give you?
So m into 2 raised to the power n.
Wait, why m times? So
Uh, m times, why so? Because one string can be mapped to one out of the m number of the possibilities.
right. Okay, so okay, let me write it. So for any x, mm, possibilities for fx, right? So number of functions, uh, product over x in 0, comma 1 to the n, m, right?
Yes,
And what is this? This is m times m times m 2 to the n many times, right?
yes.
Because the size of this is 2 to the n. And what is this?
Oh, I see. Yeah.
Yeah,
So I mean, one string can be to the m number of the times. Second can also be mapped to m number of.
right.
Yes, yes. In that
Yeah,
sense,
so
yeah.
so this is just a function. This is not a permutation or a 1 1 function, right? So I don't
Oh,
need to put m minus 1 over here.
yes,
Yeah. So is this fine?
yes, yes.
Okay, so the next question is, suppose there are 100 questions in an exam. Each question gets 1 point, each for the correct answer, and 0 points for an incorrect answer. A class of 40 students takes the exam. Suppose that each question is correctly answered by 30 out of the 40 students. Out of the following, which of the statements can be correctly inferred? Select all the correct options. The answers are options are there is uh, there is a set of 30 students, each of whom gets 100 points. There is at least one student who got 75 points or more. There is at least one student who got 100 points, and all students got 75 points. So this needs to be sort of worked out, but what would be your guess? Which of these are correct?
So there are 100 questions in the exam, and for the correct thing, it is one, and zero for the incorrect one.
Right.
And 40 students take the exam, and each question is correctly answered by exactly
75
30
students.
students.
Exactly 30 students. Right.
Exactly 30. So clearly, since the number of the students won't be same, so therefore the first option cannot be correct. That, I mean, the same set of the 30 students every time they score the
Yeah.
correct thing. So now we have to find that, I mean, what are the possibilities of different 30s out of the 40s.
Right.
So there is at least one student. So in how many ways can we select, say, the 30 students out of the 40 students, and would be
Okay,
attempting to,
let me do this. So
yeah.
B is correct, but proving B is correct requires some work. So first, can you rule out A, C, and D?
So A has been ruled out, and there is
Right.
at least one student who got 100 points. So if one student got the 100 points, means that there is definitely one student which is the part of all the 30 selections, and which is not necessary.
Okay, yeah, that is true.
Yes, so therefore this can be yes, again can be denied, and all the students got 75 points each. It shows that yes, so I mean every if every student got 25 each, so but then there would be few students. There would be only two students. So if
Okay,
all
your
the
voice broke
students
again.
got 75 each, means there is no student who could score. There exists at least one student who could score more than 75, and that can always be a possibility. That there exists at least one student who scored more than 75.
Yeah, so that is also true. Yeah, so now
Yeah.
just let me like okay, so let me formally prove that A, C, and D are false first, and then we can go to B. And the way to
Yes.
prove that A, C, and D are false is just give an instance that satisfies all the conditions in the question, right? So 30, 70, sorry, 100 questions, and each question are correctly answered by 30 students. Okay, so A is false because students. So consider this case where students 1 to 30 answer. Okay, let me write this on a new line. Can I? Students 1 to 30 answer questions 1, 5, 9, and so on. I questions of the form 4n plus 1 correctly. Okay, students 31, okay, sorry, 11 to 30, 40 answer questions 2, 6, 10, and so on. So of the form 4n plus 2 correctly. And students 21 to 40 and 1 to 10 answer questions of the form 3, 7, 11, and so on. So 4n plus 3 correctly.
So what is n here?
Oh, so okay, that I'll ask you at the very end because yeah, finding out the range for n would tell you whether the situation I'm describing satisfies the property that every question is answered correctly by 30 students.
Okay.
Sorry.
Okay.
Yeah, okay. So, students 31 to 40 and 1 to 20 answer questions 4, 8, 12. So of the form 4n correctly. Okay, let me write 4n plus. Okay, so now the first question is, does the situation that I've described over here uh, satisfy the property that every question is correctly answered by 30 students?
So yeah, so in fact this range came out to be ranging starting from 1, 2, 3, 4, and then this sequence goes like 5, 6, 7, 8, and then 9, 10, 11, and then
Of
4n
what
plus 1.
n?
So what this n here is, so 4n plus 4 is equal to 100.
Right.
So n is equal to 96 divided by 4. and 96 divided by 4 came out to be how much? 24.
24. Yes.
So yeah, n is 24 here.
Yeah. The smallest value is 0 because 4 times 0 plus 1 is 1. And the
Yes.
largest value is 24. So there are 25 distinct values of n.
I did not understand this thing.
Oh, so the smallest value of n is 0. The highest is 24, right?
Why 0? Because see,
This is
uh,
1.
start reading the numbers column wise. So here all the questions have been covered. One, two, three, four, column
Hmm.
wise. And next
Right.
5, 6, 7. So in total, our journey ends to 4n plus 4.
Okay.
So therefore, it shows that 4n plus 4 is equal to 100. So
Right.
therefore, the value of n here is equal to 24. It is fixed 24.
No, 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 no,
And
no, no. Okay. So what? Okay. The value of the range of n is 0 to 24. Why? Because, okay. So over here, you have 4n plus 1, right? Put
yes,
0 over here, you get 1. Put 1 over here, you get 5. Put 2 over here, you get 9.
uh,
Okay, okay,
uh,
okay. Okay, wait, wait. There is no comma over here.
yes, yes,
Okay,
yeah.
so by this I mean that these questions have this form. So these numbers look like these. So what I mean is every number in this sequence looks like 4n plus 1 for some n.
Yes, yes. And this count should be, since this count should be equals to what? It should be equals to, say, 100.
Right?
So therefore, 4n plus 1 is equal to, doesn't make sense.
Okay, okay,
Actually,
okay, okay. Let me remove this from here. Okay, so I'll write that later when we need it. Okay, so first of all, are all questions covered over here?
yes. So
Okay,
all questions have been covered here because I am counting the questions column wise, not row wise.
okay, right.
Fine. So one,
And
2, 3, 4, 5, 6, 7, 8, and in this way continue.
right,
And so it shows that all the 100 questions have been covered. Uh, but can you show the problem formulation once again, wherein you
okay,
asked that yes, so
uh,
each question
okay,
is answered by uh, suppose that each question is correctly answered by 30. Okay,
right.
so
So
30
is this
students would be
satisfied?
attempting. Yeah, 30 would be attempting 100 questions.
No, 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 no. So all
Any
students attempt all the questions, but only 30 students get. So for every question, there are exactly 30 students who get that question right. So 10
yes,
okay. So pick any I in 1 to 100. 30 students got that question correct. 10 students got that question wrong.
right,
So
right.
we have covered all the 100 questions. Now what I'm asking is, in this situation, is it satisfied that every question is correctly answered by 30 students? Okay,
Yes, because every question is appearing is appearing in a set. I mean all the sets are mutually exclusive here.
right. So
So
basically, pick any question of the form 4n plus 1. Okay, I don't even need 4n plus 1 now. So pick a question. If if it lies in 1, 5, 9, and so on, then 1
yes,
to 30 would have answered it correctly. 31 to 40 would have answered it incorrectly, right?
yes,
Similarly, if the question is in 2, 6, 10, and so on, then 11 to 40 would have answered it correctly, and 1 to 10 would have answered it incorrectly, right?
right.
So every question is correctly answered by exactly 30 students. That is satisfying.
Mhm.
Okay, so now what is the score of each? Okay, let me write the question of each student. Yeah, so what's the score of each student? Say, what's the score of student one?
So yeah, so student one answered. So it depends on that till what sequence this will continue. So you rightly said that this will continue till since there are four. So
Hmm.
last one will end at 100, second last 99, third
Okay,
last 98.
okay, so
So this will end
let
at
me write
97.
those to just make things clear. Let me write those.
Yes.
100,
This and this one is
99,
99, 98.
98, and 97.
Yes. So now, how many terms are there in this sequence? Whose term is 97? So 97 minus 96, uh, and difference is 4. So how many terms would be there in this sequence? So this is AP, and so AN is equal to what that A plus ND formula. So there would be 96 divided by 4, and this value of 24. So there are 24 number of the terms. 24,
25.
20, 25.
Okay, so one way to do it was using this.
Yes, so there are 25.
Yeah, so,
Right.
okay, so that is why I had written these. So,
Yes,
okay,
yes,
every question over here is of the form 4n plus 1, right? For some n.
yes, yes, correct, correct.
What is the range of n? Well, it's from 0. So it starts at 0 because I want to cover 1, right?
Yes,
And it ends at it ends at 24 because I want to cover 100.
right.
So n can be from 0 to 24, and every value of n gives you exactly one number in the sequence, right?
Yes, yes.
And 0 to 24 are 25 numbers. So this sequence consists of 25 numbers. Okay. Each of these consists of 25 numbers. So now using this, can you tell me what's the score of each student?
So the score of the student 1 would be 1 to 30 answered 25 questions correctly
Right. Okay, so where does student 1 appear? The student 1 appears over here, and over here, right?
at 3 places, right?
So student 1 gets 75 questions correct, right?
Yes.
Similarly, look at any student. It appears in exactly three of these sets, right?
So why would a student appear at maximum 3 places or
Okay, so
minimum
let's
3
so there
places?
are just four cases, right? Student is between 1 to 10, 11 to 20, 21 to 30, 31 to 40, right?
1 to 30 is fine,
No, no. So
and
what I'm saying is every student appears in one of these four sets: 1 to 10, 11 to 20, 21 to 30, and 31 to 40, right? I can divide students in these four sets.
no. I mean, it's not clear. What did you say? I mean, your voice was
Okay,
not.
so every student, okay, so this set of students is student 1 to student 40, right? I am dividing that set into four sets: students 1 to 10, students 11 to 20, students 21 to 30, and students 31 to 40. Okay.
Right, right.
Now let me pick the first set, 1 to 10 students. Where do all of them appear? They appear over here, and over here, right?
But how did you come to know that? I mean, these four sets are possible. Uh,
Okay, so that is part of the proof. So, okay, so I could have divided the set of 40 into any way I wanted. I
huh.
divided them into these four sets to make the argument simpler. Okay,
Mhm. But then this is such an out of box kind of the thinking that I mean, how did someone arrive at this thing that okay, the set of the students should be divided in these four sets only? Somehow I'm trying to smell or view it from the pigeonhole principle kind of the thing
okay,
that
okay. So, okay, let me do it in a slightly different way. So, I want to count the. So, I want to compute the number of score of each student. There are two ways of doing that. Number one, find out how many questions each student answered correctly. What's the
Mhm.
other way?
So how many students answered the question correctly, and the other one could be the.
How many questions did the student answer incorrectly? Right. Find that
Mhm.
number, subtract from 100, you are done.
Mhm.
Okay. Okay. So, how many questions does any student from 1 to 10? Okay. So pick any student. Okay. Okay. So pick any student from 1 to 40. Like, which one would you want to pick?
1 2.
So pick any student from 1 to 40.
1 to 40. Okay, say
Yeah,
20, 20.
20. Okay. So where does the student 20 not appear?
So 20 will not appear in only at one place.
Yeah, this one, right?
So my
This one.
point here is that how is that possible that only four different sets are, you could have divided it into say like say 1 to 30 and then say from
Yeah.
31 or in some other way.
Yeah, okay. So over here, I am constructing an example, right?
Yes.
To prove that A is false.
Uh-huh.
So while I can divide students in any way I want, I
Hmm.
would rather divide students in a way that makes my job simpler, right?
Yes, yes,
Yeah, so that's why I did it like this.
yes, yes. Now,
Correct.
yeah, understandable.
Yeah,
Yeah.
yeah. So you picked the student 20. The student 20 is just not present over here, right?
Hmm.
So the only questions that the student 20 answers incorrectly are these.
Yes.
And how many are these? 25.
25.
And you could have done this for any student, right?
Yes.
So the number of questions that a student answers incorrectly is 25. So every student's score is 75, right?
Hmm.
Okay, so we have constructed an example. It satisfies all the conditions. In particular, 40 students take the exam. There are 100 questions. Each student answers 30 questions correctly, right?
Hmm.
And what's the score of every student? 75. And what does the first option say? There are 30 students, all of whom got 100. But this example proves it false, right?
Hmm.
Yeah, so A is false, right?
Yes.
Is this fine?
Yes.
Yeah. What about C?
So at least one student scored got 100. So that is not possible. That is
Yeah,
not possible.
because this exact example shows C is false, right?
Hmm.
Everyone got 75. There is no one
Yes.
who got 100, right? So
Yes.
C is false. Above example. So what about D? So in D, every student gets 75 points. So the example that we have does not prove that B is false, right?
Yes.
But so what I'll do again is construct an example for D. Construct an example which proves D false.
Hmm.
And this is very easy. This is not okay. So this example was slightly involved. The example for D is very simple. So can you try to can you take a guess?
All the students got 75 points each. So yeah.
Okay, so suppose there were 30 students,
Hmm.
all of whom got 100, then this would be false, right?
Hmm.
Okay, so here's the example. Students 1 to 30 answer all questions correctly, and students 31 to 40 answer all questions incorrectly.
Yes. So in this case, yeah.
Yeah, so 1 to 30 get 100 points each, and 31 to 40 score 0 points, right? So this is clearly not true. Yeah, so are A, C, and D fine?
Yes. Yes.
Okay, so now let's look at B. Option B is there is at least one student who got 75 points or more. Okay, so before proving, so B, okay, so this is some, so you can prove B using something called an averaging argument. So let me first state and prove the averaging argument. Okay, so the statement of the argument is the following. Suppose that sum over I in 1 to n ai is equals to b. Then, okay, in fact, let me prove a slightly more general version. There exists an I in n such that ai is greater than equals to b over n. Yeah, so is the statement of the averaging argument clear?
Yes, yes, it
Yeah.
is.
So what this says is, suppose the average of n numbers is b over n, then there is at least one number which is greater than the average.
Yes, yes.
And so you can also prove the other thing. Given n numbers, there is at least one number which is smaller than the average. So
Yes, and
basically,
this is
yeah,
this is this is somewhat related to that PSP only, the pigeonhole principle.
yeah, yeah, yeah.
That Yeah, that if we are distributing k number of the objects into the n number of the boxes, then there would be at least one box containing more than the ceiling of n by k number of the object.
Yes. Yeah, so that's one way to prove it. Another, like just one line proof is this. So what I'm going to do is by contradiction. So suppose for all I, ai is strictly less than b over n, then what is the value of this sum? This would be less, this
Less
would
than
be,
less than b.
yeah, this is equal. Yeah, because there are n summons, each and every one has value less than b over n. So the total sum would have value less than b over n times n, which is b, right?
Yes,
But this is a contradiction.
yes,
This contradicts this, right? So this is the one line proof of the averaging argument.
yes,
Yeah, but you can also prove it using the pigeonhole principle.
yes, yes.
Okay, so now that we have this, can you use the averaging argument to prove that b is true? In
So
particular,
see,
what you would have to do is you can tell me what AIs are and what B is over here,
yes. So
and what N
uh,
is as well. AI, B, and N.
yes. So AI here is equal to what? So uh, so since now all the students have got 75% each is not true,
Hmm.
so clearly its negation would be true then. So therefore one student got 75 or more. This was my original argument here.
Okay, so all students got 75 points each. That is false, right? So
Yes.
so the negation is there exists a student who did
Uh,
not get 75, but consider a situation in which every student got 74. That also satisfies the negation, right?
yes.
Yeah, so
Yeah.
you can't just negate D and come to B.
Yeah. True. True. So now there exists so at least one student who got more than 75 or more. So yeah.
Okay, so first of all, clearly 75 over here is B over N, right?
Mhm.
Okay. And we have to somehow figure out what AI, B, and N are. So okay, here's one way to do it. Let AI, okay, let N be 40. Let AI be the score of student I. Okay, why are we picking AI to be the score of student I? Because what do we want to show? We want to show that one student got more than 75.
Yes.
75 is B over N. So we need, so, and we can show that AI is greater than B over N, right? So if AI were the score of a student, we would be good, right?
Yes.
So let AI be the score of student I. Okay, so now the question is, what is sum over I in 1 to N AI? So
So
we need to compute this to divide this by N, right?
yes,
Okay,
we
so
need to, yeah.
yeah, so and
So se-
generally, yeah, go on.
so 75
Okay, your voice broke.
seven yeah, 75 we add 75, and how many times we add 75? Say 40 times.
Okay, why do you add 75? How are you getting the 75?
Because 75 is the value of b by n.
Okay, no, okay, so we want B by N to be 75, right?
Yes.
So we'll have, okay, so and how are we getting B? We are getting B from here, right? So over
Hmm.
here we are setting, so our goal is to first show, okay, so our goal is to show that B by N is 75. So we would have to uh, prove that sum over I in 1 to N AI is greater than equals to B, whatever B may be, right?
Hmm.
Okay, so AI is the score of the ith student, right? So
Hmm.
what is this? This is the sum of scores of all students, right?
Hmm.
Okay. So my claim is this is 30. Okay, is this is 100 into 30. Why? Because each question is answered correctly by how many students?
30.
Right. Okay, so and whenever a student, okay, and every correct question contributes, so every correct question, so rather I should say, so every question contributes to how many of these AIs? And there are 100 questions. Okay, so each question is answered correctly by 30 students, right? So my claim is every question contributes 1 to exactly 30 of these AIs. So is this claim fine?
What did you say?
Yeah.
Can,
So in the question, we have that each question is answered correctly by 30 students. And
hmm.
from this, I'm claiming that each question contributes 1 to 30 of these AIs. Why? Because whenever a question is correct, the score is 1, right?
Yes, yes.
And 30 of these got it right. So for 30 many AIs, I don't know which 30 many, but for exactly 30 many AIs, every question contributes 1, and for the remaining 10 many AIs, the question contributes 0, right?
Yes.
And there are 100 questions, so the total contribution of all questions combined would be 100 times 30, right?
Yes.
So this was another way of finding out the score. Sorry, the sum of scores.
Right. And
Yeah. So okay. So basically, what we did was this.
mhm.
So there are students one, 2, 3, and so on, right? And questions. Okay. Questions 1, 2, 3, and so on up to 100, right?
Mhm.
Now, what's one way to find out the sum of scores of the students? Okay. First of all, okay, and what I'm going to do is I'm going to write one blue color. So I can write 1 or 0 in this table to determine whether the question was correct or wrong, right? So
Mhm.
student, okay, let me write student over here. Okay, so one way to compute the number of one way to compute sum of AI is the following. First of all, sum of AI is just the sum of all the entries in this matrix, right?
Yes, and moreover, there should be minimum 30 number of the ones, or rather exact 30 number of the ones in a column.
Right. Yeah. So I'm getting to that. But so the number of AIs, sorry, the sum of AI is the sum of all the entries in this matrix, right?
Yes,
Now there are two ways to compute the sum of and sum this sum, right? We can find out the value of each and every column, sorry, each and every row, and add them, right?
yes,
Another way is find out the value of each and every column. So find out this sum and add them, right?
yes,
And this is exactly what we did over here. Why? Because as you said, okay, let's look at this column, right? There are going to be exactly 30 many ones in this column, right?
hmm,
And there are 100 such columns, so 30 times 100.
yes,
Yeah, and you would find something like this type of a table and adding rows and adding columns type of argue approach. There are a lot of places where you use averaging arguments.
yes, yes,
So
yes,
in particular, our quantities AIs were these sums, right?
hmm,
And to compute their sums, we used columns. So our quantities corresponded to row sums, but to compute their sum, we used column sums.
yes,
Yeah. Okay, okay. So this is not required for the proof, but yeah. So, okay. So now we have that sum of all the AIs is 3000, right?
hmm,
The sum of all the AIs is 3000. So averaging argument tells us that implies there exists an I such that AI is greater than equals to 3000
by 40,
divided by 40,
40,
which is 75.
yeah,
Yeah. So this proves B.
yeah.
Yeah.
Pretty long question, but then
Yeah.
I was just wondering that how this question is related to this computational complexity course.
Okay. Okay, use averaging arguments in a lot of places for randomized algorithms.
Okay, okay,
Yeah. Okay. Okay. So basically, to let's say bound something for randomized algorithms, like running time or success probability or something like that.
okay, okay, yeah,
Yeah.
great, yeah,
And
yeah.
it's also used at it's basically used whenever you need to count something and often upper or lower bounds on them.
Yes,
Yeah.
yes,
More generally. Yeah. So is this fine?
yes, yes.
Yes. So then let's look at the next problem. So yeah, now let's look at this year's week 8 practice assignment. And the first problem is there is a language in P space that is not computable by constant depth polynomial size circuits using AND or AND NOT gates, true or false.
Yes, so if there is a language in the P space, so okay, so consider a which does not use polynomial size. So
Right.
if the space occupied is polynomial, then will it not refer to that the circuit will also occupy the polynomial space only?
No, 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 no. So that okay.
Not
So
necessarily.
yeah. So that's what the problem. So the answer is true. And in particular, we know this. So parity. So the language is this X such that parity. Okay. Number of ones in X is odd, is not in AC0, which is the class of computable by constant depth, polysize circuits. Yeah, so okay, so this theorem is known that the language parity cannot be computed by constant depth polysize circuits. So if we can show that parity is in P space, we are done, right?
Is
Oh, so your voice broke. Can you repeat that?
yes. So my question is that how this parity is related to p-space thing?
Okay, so this is just a language, and we know
Uh-huh.
that this language cannot be computed by uh, constant depth polysize circuits. So if we can somehow prove that this language is in P space, we have a language in P space which cannot be computed by constant depth polysize circuits, right?
So parity is in the p-space. We just need to find whether the number of ones is odd or not.
Yeah, so in fact, it's in order one space. You just need to make one pass over the string and store
Yes.
one bit, which is the number of ones till that place, right?
Yes.
Yeah, so parity is in P space, and so you have a language in P space which is not computed by uh, constant depth polysize circuits. So this is true.
Okay. Okay.
Yeah. Okay, so the next question is,
By
let
the way,
D be
here
this.
this AC stands for what? Arithmetic circuit or
No,
something
no, no, no.
else?
AC stands for alternating circuits.
Alternating circuit. And
Yeah.
this
So
zero here stands for
okay.
zero as a
So
superscript.
ACI, where I is some number, is a s- is a class is a set of languages decided by the class of uh, order log depth polysize circuits. So
Okay.
ACI
Okay.
is a class of all languages decided by circuits whose size is polynomial and depth is order log to the in. When you put zero, you get constant. So AC0 is the class of all languages computable by constant and polysize circuits.
Okay. Okay.
And
I
these are called
see.
alternating circuits because in these circuits you have, I mean, okay, so given such a circuit, you can convert it to a very nice form where you have all the NOT gates at the bottom and then you have alternating gates of AND or AND and NOT and OR gates.
Okay. Okay.
Yeah, so that is why it's called alternating circuits.
Okay.
Yeah. Okay. So the next problem is let T be the set of all univariate polynomials Px over F3 of degree at most 10. What is the probability that one is a root of the polynomial Px chosen uniformly at random from the set T? Enter the answer in numerical form. Okay, so I won't ask you what the answer to this is because this needs to be worked out. Okay, so yeah, let's work this out. Yeah, okay. So a polynomial Px over F3 at most 10 looks like. Okay, so can you give me a general expression for a polynomial of degree at most 10?
Degree at most m would be like say a raised to the power m plus something say c1 a raised to the power m minus 1 and then so on. But since here coefficients are defined over f3, so these
Right.
AIs can take the values from 0 to 2.
Okay, just a second. One of my earphones is not working, so let me first fix that. Yeah.
So it would be uh, like say something say a1 x raised
Mhm.
to the power 10 plus a2 x raised to the power 9 and then so on. The degree is at most 10 and these
Right.
AIs can take the values from 0 to 2 since it is defined
Right.
over f.
Yeah.
Yeah.
Okay, so it looks like this. A10 x to the 10 plus A9 x to the 9 plus A1 x plus A0, where A1 to A0 are in F3. Right.
8 to A0. Yeah.
Oh, yeah, yeah, sorry, A10. Okay, so now uh, 1 is a root of. So when is 1 a root of 3x?
So it becomes 0. This thing becomes 0.
Right. 0 where?
When the value of x becomes 1.
Exactly. So when A10 plus A9 plus A0 is 0, right?
Yes.
Okay. So now we are picking Px uniformly at random from the set D, where D is the set of all polynomials of degree at most 10, right?
Hmm.
So what does this mean? My claim is picking Px uniformly at random from D is the same as picking A0 to A10 uniformly at random from F3. So does this claim make sense?
Yes, yes,
Yeah, because how do you construct P? It's this, right?
yes. And
So
it is same as picking these coefficients such that their sum came out to be 0.
no. Okay, so that is what the question asks us, right?
Yes.
So right now what I'm saying is forget about the question.
Hmm.
What does it mean to say that Px is uniformly at random from D?
Yes, yes.
Yeah. And the reason is okay, so uh, Px uniformly at random from D means that every polynomial in D has an equal probability of being picked, right? Now any polynomial in D looks exactly like this.
Hmm.
And so if I were to pick A0 to A10 uniformly at random, what would be the probability of any polynomial from D being picked? It would be 1 over 3 to the 11 because there are
I could
11
not,
numbers, right?
I could not understand this. How how
Okay.
how did you get this value?
Okay. So what I'm doing is, okay, so first of all, okay, let me prove this. What's the size of D? Size of D is 3 to the 11, right? Because size of D is equal to the number of A zeros times the number of A1 times the and so on times the number of A10, right? And each of
Yes.
this is 3. Okay, and so picking Px uniformly at random from D means that every Px must have a probability, must be picked with probability 1 over 3 to the 11, right?
Correct.
Yeah. And when A0, A10 are picked. Okay, what's the probability of Px being B0 Yeah, so any polynomial in D looks like this, right? B0 plus up to, okay, there is a 10 over here. So any polynomial in D looks like this, right?
Yes.
And when we pick the coefficients A0 to A10 uniformly at random, what is the probability that Px would be this? It's the same as the probability that A0 is B0, A1 is B1, and so on, right?
Yes.
So B0 is some number between 0, 1, and 2, some number from 0, 1, and 2, some fixed number from 0, 1, and 2, right?
Yes.
But I'm picking A0 uniformly at random from 0, 1, and 2. So the probability that A0 and B0 are the same is 1 over 2.
Yes.
Same for all I, right? And I'm doing this independently at random, right?
Yes.
And there are 11 many of these, so 1 over 3 to the 11.
Yes.
So yeah, this probability is exactly what we wanted over here, right?
But then this is the probability of selecting, say, 11 number of the coefficients. That's it.
Right? Yeah, and
One
11
one one
coefficients
one.
exactly corresponds to a polynomial, right?
Yes. And but then the one would be the root if the sum of those coefficients
Okay, okay,
cannot
so
be
okay,
zero.
so we are coming to that right now. Mike, what I was trying to prove was this. So I made this claim that picking a polynomial uniformly at random from D is the same as picking the coefficients uniformly at random from F3. So far, I was just
Yeah.
proving that. Okay,
Yes. Yes. Yes.
so now we have this description of what it means to pick a polynomial from D. Then we can go to the question, right? Okay, so now let's look at the question. So probability uh, A0 to A10 picked uniformly. Okay, let me write it like this. Probability Px picked uniformly at random from D. Uh, 1 is the root of Px. This probability is the same as probability Px picked uniformly at random from D. P of 1 equals to 0, right? But because of what we just showed, this is the same as picked uniformly at random from F3. A0 plus A1x plus up to, sorry. Yeah, okay, so P looks like there. Uh, yeah, so what is the root of Px if and only if this sum is 0, right? Yeah, so over here, I change this to this using what we proved over here, that picking P uniformly at random from D is the same as picking A0 to A10 uniformly at random from F3. So that is how I went from here to here. Is this fine?
Yes. Yes.
Yeah.
Yes.
And I changed this to this by using what we proved over here.
Yes.
Yeah. So are you convinced that these two probabilities are the same?
Uh,
These
yes,
two.
these two probability are same. I mean,
Yeah.
basically, we are looking for the probability of having the values of these coefficients is equal to zero out
Right.
of the 3 to the power 11 number of the possibilities.
Yes. Okay. So now, how would you compute this probability? Okay. So one way to compute this is the following. Okay. Okay. So what I'm going to do is I'm going to condition now. So probability A0 to A10. Okay. Let me note this. Sum overall A0 to A9 in F3. Probability A0 A0 plus A10 is equal to 0, conditioned on A0 is equal to B0 up to A9 equals to B9 times probability uh, A0 equals D0, A9 equals B9. Yeah, so does this equality make sense?
Not much, not much. So basically, we are looking for that when the sum of these coefficients would be equal to zero. Given that, so whatever evidence is given here, how does it make sense that a zero is equal to b zero and a1 is equal to one?
Okay, okay. So suppose that, okay, so I want to find out what is the sum of A0 to A10, right? So let's
Yes,
fix A0 to A9.
zero to.
So let us fix A0 to A9 to be B0 to B9. Okay. Suppose someone told you that when I picked like this, I got A0 is equal to B0 and A9 equal to B9. Okay. So I got this. Suppose someone told you this.
Okay, okay.
Then what is the probability of this being zero? It's exactly this, right?
Yes, so this is a conditional probability that thing. Yeah, fine.
Right. And okay, what are the possible values of A0 to A9? So here I had fixed the value of A0 to A9 to be B0 to B9, right? So
Uh-huh.
what are all the possibilities? It's B0 to B9 in S3, right? So basically what you are doing is the following. Uh, you are assuming that A0 to A9 are B0 to B9, then computing this probability for all B0 to B9, right?
Mm-hmm.
And this gives you the this sum. Okay, so let me explain this with an example. Suppose let's just look at A0 plus A1 equals to 0, right?
Uh-huh.
So this is the same as probability A0 plus 0 is equal to 0 times probability A1 is equal to 0 plus probability A0 plus 1 equals to 0 times probability A1 equals to 1 plus probability A0 plus 2 is equal to 0 times probability A1 equals to 2, right?
Yes.
Yeah, and that is exactly what I'm doing over here because I could have written this as probability A0 plus A1 equals to 0 given is A1 equals to 0, right?
Yes. Yes.
Yeah, and that is exactly what's happening over here. But instead of A1, you now have 10 variables, A0 to A9, right? So what we did
Actually,
over here was we went
yeah.
over all values of all possible values of A1.
Yes.
So over here we have to go over all the possible values of A0 to A9, right? The vector A0 to A9,
Yes.
which is exactly this because A0 can be anything, B0, A1 can be anything, and so on, right?
Yes, now I understood. I forgot
Yeah,
to see this summation thing here, and yeah,
right.
it's clear to me now. Yeah.
Okay, so if this is clear, then okay, can you tell me what this probability is for any B0 to Bn? Okay, so
How would I know this probability that yeah, these two
yeah, okay,
coefficients? Yeah.
let me rewrite it. So let me rewrite this in a form similar to this, then it might be easier. Okay, so we are given that A0 is B0 and up to A9 is B9, right? So I can replace A0 by B0 is equal to minus A10, right? Okay, mm, let me write it in the form that's the easiest one. A10 equals to minus B0 plus B1 plus B9 A0 equals to B0, A9 equals B9. Okay, so what I'm claiming is this probability is the same as this probability. Why? Because I can put B0 to B9 in the place of A0 to A9, right? Just as I done over here.
Yes. Yes.
And what I would get A0, sorry, and I would get B0 plus up to B9 plus A10 is equal to 0, right?
Yes.
So I can take B0 to B9 on the other side, but I have to do mod 3 because I'm working over F3,
Yes. Yes.
right? So this makes sense, right?
Yes.
Okay.
And even calculating this probability that A10 is equal to minus of this thing is not easy.
Okay, this is very easy. And the reason is the following. What are B0 to B9? They are fixed.
They are 0, 1, 2, and 3. Three
No, no, but
possibilities.
right. No, 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 okay. So that is true over here. But once I move inside the summation, I have conditioned down B0 to Bn, right? So now B0 to Bn are not random variables that are they are numbers, right?
Yes.
So this summation is going to be some number between 0, 1, and 2, right? This entire thing is going to be between 0, 1, and 2, right?
Ah, so here this is the difference.
Oh, your voice broke.
Equal to, yeah, A10 can have only three possible values. So therefore, this probability will came out to be uh, 1 by 3.
Exactly, yeah. Because this is a fixed number, and the probability
Your
that
video
A
got
is
freezed in case.
yeah, okay. Okay, so I think I lost connection. Let me try to reconnect. Okay, can you hear me now?
Yes, yes.
Okay, my screen is not visible, right?
Yes.
Okay, so let yeah, so is my screen visible now?
Yes, visible. Visible.
Yeah, okay, yeah,
Yes, yes.
yeah, great. Yeah. Okay, so yeah, so as I was saying, this is a number between 0, 1, and 2, right? And since we are picking 8 and uniformly at random from 0, 1, and 2, this probability is 1 over 3, right?
Yes.
Yeah, so this is 1 over 3. I'm just taking this is 1 over 3 regardless of what B0 to B9 is, so I can take it out common, right?
Mhm.
Yeah, so I get this, right?
Yes.
So now what is this summation? The value of this summation?
So how to know that what's a probability value of uh, this term
Okay,
is?
that's one way of doing it. So, okay, let me first tell you a direct way of doing it, and then I'll do it the way you are saying. Okay.
Right.
So I'm going over B0 to B9, all B0 to B9, right?
Yes.
Now A0 is okay.
So
A0, okay,
for
let
A0,
me add
for
this over
A0 we
here.
have for A0 we have three possibilities, and for all the A's we have three possibilities.
Right,
So in fact, this came out to be the joint probability thing,
right,
and so therefore for A0, since we have three possibilities. So 1 by 3, and then so this value came out to be 1 by 3 raised to the power 10.
Okay, that's one way of doing it. So another way is this. So over what is this? So this is the sum over all possible values, right?
Yes.
So A0 to A9 can only take a value in this set, right?
Mm-hmm.
So this is one. This whole thing is one. Because okay, summing up over all the okay, I'm doing something like this. Suppose A were a number and A would be between 1 to 10. Asking what I'm asking over here is something like this. Sum of probability A equals to 1 plus probability of A equals 2 plus probability of A equals 3 and so on, right?
Yes.
So this has to be 1, right? Because the sum of because the total probability has to be 1. So this is one way of doing it. If you don't want to do it this way, then we can do it as you suggested, right? So this is 1 over 3 to the 10, right?
Yes. Yes.
Yeah.
Yes.
Okay. And so, okay, times 1 over 3 to the 10 times sum over V0 to P9 F3 1, right? So now what's
Yes.
this value?
So we are adding one, how many times? Say here we are adding 10 times.
No, not 10 times, right? So we are adding 1 for every possible value that B0 to Bn can take, right? So B0 to B9 can take.
Uh-huh.
So, okay, how many possible values can B0 take? 3. How many possible values can B1 take? 3 and so on, right? So, how many
Mm-hmm.
possible values can this vector B0 to B9 take?
So 3 raised to the power 10.
Right. So, we are adding it 3 to the power 10 times, which is just 1 over 3, right? Yeah, is this fine?
Yes.
Yeah.
Yes.
Okay, so the answer is 1 over 3.
This is very interesting problem.
Yeah. Yeah, I mean, in randomized, like in randomized algorithms, you would find such like questions where you have to bind count probabilities, and yeah, you need to condition them. So yeah, at least for me, the main part of this proof was this conditioning.
Yes.
Yeah, and I mean, intuitively, this conditioning makes sense, right? I want to find out what's the probability that 10, 11 numbers sum to something. Okay, fix 10. Then my task becomes really easy, right?
Mm-hmm.
And yeah, this is just the way of formalizing that fix 10, look at what happens next.
Yes.
Yeah. So if this is fine, let's look at the next problem. Okay, so the next problem is that K, M, comma, N with a complete graph, bipartite graph defined in the previous question. So it's not defined, I'll define it later. Suppose M is greater than N, then what is the number of perfect matchings in the graph K, M, comma, N? Mn, M to the N to the M factorial, N factorial over N factorial, none of these. So Kmn is this. Uh, is L is joint union R E, where L is M, R is N, and E is sorry A I N. So it is a bipartite graph where the left set has M vertices, the right set has N vertices, and there is an edge between every vertex in the left set and every vertex in the right set. Okay.
So for the first vertex in the left hand side, we have n number of the possibilities. For the second one, n minus 1. And then
Okay,
for the third one, n minus 2. And in the left hand side, we can consider, say, for the since the value of m is greater than n,
right.
so yeah, so we can count up till n number of the elements here only till this thing.
Yeah.
So uh, I could have
And
given factorial n as the answer, but then factorial n is not one of the possibility here.
so can you repeat m factorial?
So for the first vertex in the left
No,
hand
no.
side,
So
we have
I heard that. What was your answer? Your right, like your final term, m factorial?
yes, factorial n, because m is greater than n, so we can only consider n number of the possibilities. I mean, we can only consider n number of the vertices in the left hand side
Okay,
out
okay,
of the n number of the vertices.
okay. So for one in, so the first vertex in L, uh, there are m possibilities, right?
Yes.
M possible vertices.
So yes, yes, yes. Factorial m.
Sorry,
Yes,
sorry,
yes.
n,
Yeah.
n. So there are n edges, right? M for
Yes.
possible vertices in R. For 2 in L, there are n minus 1 possible vertices in R, right?
Yes.
And so on. And so for actually, no, this is not the right way of doing it. Yeah, no, 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 no. So okay, we can't do it from starting from L, right? We should do it starting from R.
Why?
Why?
Why so? Because
Okay, so if I were to do it like this, okay, let me first do it like this and then tell you why this is wrong.
yes, yes, you're right. Yeah. So because the
Yeah,
value of m is greater than n. Yeah.
right.
Fine.
Because what we are forcing over here is the following. We are forcing the perfect matching to match the vertices in R to the first n vertices in L, right?
Yes.
So
Yes.
this is the wrong way of doing it. Because the right way is for 1 in R, there are m possible value vertices in L, right?
Yes.
For 2 in R, there are m minus 1 possible vertices, and so on. So what n in R, how many possibilities would be there? M minus n minus 1. Because n minus 1 have already been taken, right?
Yes.
Yeah. Okay, so the number of perfect matchings. So what is this number? This is m times m minus 1 times m minus 2 times m minus n plus 1, right?
Will it be factorial of m divided by factorial of n?
Um,
No, 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 no,
okay.
no.
So this is m times m minus 1 times m minus 2 times m minus n plus 1 times m minus n times up to 1 divided by uh, m
M
minus
minus n.
n minus 1 up to 1, right? Yeah, so I just
Yes.
multiplied and divided with this quantity, right? So now the numerator is n factorial. And what's the denominator? The denominator is, yeah, so the denominator
Yes.
is m minus n factorial, right?
Yes.
Yeah, and this is not there, so it's none of the above. Yeah. Is this fine?
But this is an interesting result. Yes,
Yeah.
yes.
Okay. And so if you were to put m equals n, then you would get n factorial, right? Which is what you would expect if your graph had same but equal number of vertices on both sides.
Yes.
Yeah. Okay, so select all the correct statements from the options. Uh, RP is contained in P slash poly, co-RP is contained in P slash poly, BPP is contained in P slash poly, and ZPP is contained in P slash poly. So which of these are correct? So, okay, what we know is this. So BPP, so this is what we know. And using this, can we say which of the options are correct?
So yeah, yeah, last time also we discussed this thing, the relation in between the different
Right.
probabilistic classes. So
C is
this is a
clearly
known
correct.
result.
Right.
ZPP is there at the intersection. I forgot those relation actually.
Okay, so yeah, the relations are this. ZPP is equal to RP intersection co-RP, and both
Yes,
RP and co-RP are in BPP. Yeah, then since BPP is in P slash poly, RP is in P slash poly, co-RP is in P slash poly, and ZPP is
yes,
in co everything is in P slash poly.
yes.
Yeah. So now let
And what's the meaning of this thing that BPP is a subset of PY poly that we do have a
poly right.
polynomial
Yeah,
size
go ahead.
circuit.
Yeah, polynomial size circuit families.
Polynomial
So
size
okay,
circuit.
families because so language corresponds to a family of Boolean functions, which corresponds to a family of circuits, right?
Mhm.
Not just one circuit, because for every n where n is the length of the string, you would have a different Boolean function.
Okay, okay.
Yeah. Okay. So the next problem is suppose P equals RP, the then polynomial identity testing has a deterministic polynomial time algorithm, true or false.
So if P is equal to RP, so
Okay. First of all, what do we know for PI polynomial identity testing? Like uh, which class is it in? Okay. So we know this. Right. So we know this is in co-RP.
mhm.
Yeah, so now if P equals RP, what can we say about polynomial identity testing being in P?
So if P is equal to RP, then
Right. Okay, so P equals copy, right? So if a
yes,
language is in P, its complement is also in P.
yes,
So P equals RP implies P equals co-RP, right? Because copy equals co-RP and copy is the same as P, so P equals co-RP.
okay,
So polynomial identity testing is in P, and that therefore it has a deterministic polynomial algorithm, right? Yeah, so it's true. So is this fine?
yes, yes.
Yeah. So now, okay, we have 10 minutes. So let's see how many of these can we do. Okay, I think we can probably do the first two. Yeah. Yeah, so now let's look at some of the questions from this year's week 7 assignment. So before that, if you have like any doubt in one of the questions, you can tell me and I can solve just those questions first. I'll just wait for a minute or so in case you have a doubt in some question. Otherwise, I'll just solve the first two questions.
So in this week,
Yeah.
what are we solving? This week's eighth assignment or last week's assignment?
Oh, so I your voice broke. Can you please repeat it?
I could not hear you.
Oh, so your voice broke. Can you repeat what you just said?
Yeah. So what are we solving in this? I mean, in this session, the eighth assignment of this week and
No,
the
no. So the eighth assignment from last year.
uh-huh.
Okay, so we first all eighth assignment from last year, then pra- uh, the practice assignment for week 8 from this year. So
Okay.
yeah, and now we are solving this year's week 7 assignment.
Okay.
Yeah, yeah. So okay, so if there are no preferences for any questions, let me just do the first two questions. So the first question is at
So
CBS,
actually, yeah, yeah.
yeah,
I want to understand this sequence that in the next week we would be discussing the ninth assignment of
last year and
uh,
eighth assignment of this year. Okay, so okay, not exactly. Ninth assignment of last year,
uh-huh.
ninth practice assignment of this year, and eighth assignment of this year.
Okay.
So
Okay.
basically, we would only discuss an assignment this week if its deadline has passed. So in week 8, we would discuss week 7 assignment from this
Yeah.
year. Yeah,
Yes.
yeah. So the first question is, let's see be a circuit where each gate has fan in at most 3 and fan out uh, exactly 1. The depth of the circuit is 5. Then the number of gates in the circuit would be at most what? So I won't ask you what this is because this needs to be worked out. But okay, let's try it. So C is a circuit where each gate has fan in 3 and fan out 1, right? So first of all, let me draw the output gate of C. It has fan out 1. Now, how many gates can feed into this output gate at most?
Hmm. So three. I mean, the
Yeah.
value of the pen out uh,
The value of fan out is 1. The
is
value of fan
exactly
in
one.
is 3, right?
The value of fenin is three. So maximum three gates can feed into this gate,
Right.
and one can go out. Yeah.
Yeah. So now, okay, let's look at any one of these three gates. How many gates can feed into that gate? So let's focus on this gate. How many gates can feed into this gate?
How many gates can fit into this gate? So
Yeah.
three.
Yes, exactly. So 3. Okay, so the depth of the circuit is 5, which means it has 5 levels of such gates. Okay.
Mhm.
So number of gates in level 1. So I'm calling this level 1. The topmost level I'm calling it 1. This I'm calling 2. This I'm calling 3. How many
Yes.
gates are there in level 1? 1.
One.
How many gates can be there in level 2? Okay, why
Three.
am I at most 3, right?
Yes.
Yeah. So okay, then how many gates can I have in level 3?
Three into three into three. Nine.
Yeah. Similarly, gates in level 4, 27. Okay, let me do it like this. So in
Can we write it?
level 3,
Yeah,
there
as
are
the
3
power of two.
square. Yeah. So this is 3 to the 4, right?
Yes.
So number of gates is at most 1 plus 3 plus is 3 to the 4. Okay, so what's one way to evaluate this expression without using a calculator?
GP. It's a GP.
Yeah.
Yeah.
So what's the formula?
So A, the one, and then
Hmm.
3 raised to the, how many terms are there? 0, 1, 2, 0
5.
to 4. 3 is to power 5 minus 1 and divided by the 3 minus 1.
Yeah. Uh, 3 to the 5 is 81 times 3, 243. So this is 1 to 1. Yeah. Is this fine?
Yes,
Yeah.
yes.
Okay, so the next question is, okay, 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 let's do this question very quickly. So the next question is, which of the following functions are monotone? Remark all the correct answers. The first is majority. The function outputs 1 if and only if sum over I in 1 to n, xi is at least n over 2. Parity, connect G, where given an undirected graph G on n vertices, connect G will be 1 if and only if G is connected. And here the input vector contains the n choose 2 entries corresponding to each possible edge. So you are sort of giving the first half of the adjacency matrix, which is enough to describe a graph if it is undirected, which in this case it is. And the last is intersect x, and this function is 1 if and only if the sum over I in 1 to n xi yi is greater than 1. Again, this needs to be worked out. So let's look at all the options. So first of all, yeah, f is
So,
monotone if x less than equals to y implies f of x is less than or equals to f of y. And by x less than equals to y, what I mean is this. Okay, x less than equals to y. So this is how it's defined. For all I in n, so I'm assuming that x and y are n bit numbers. So uh, xi is equal to 0. Okay, no, no. Okay, so x is less than equals to y if for all I in n, the ith bit is smaller. So if in particular if xi were 1, if xi were 0, yi could be anything, but if xi were 1, yi has to be 1.
yes.
So this is the definition of monotone function. Okay. Now my claim is this: f is monotone if uh, x less than equals to y implies, okay, if so what I'm claiming is a function is monotone if and only if it satisfies this property. Why? Because okay, if x is less than equals to y, we want fx to be less than fy, right? Suppose fy fx were 0, then fy could be anything, right? It can be 0, it can be 1, doesn't matter, right?
Yes.
But if fx is 1, fy must be 1.
Right.
Yeah, so we can say that f is monotone whenever this happens, right? So now let's look at all the options. Okay, so majority is equal to 1 if and only if sum over I in 1 to n xi were greater than equals to n over 2, right? Okay, so now so if yi, okay, so if I flip, okay, well, let me write it like this. So if x is less than equals to y, what does that mean? That uh, whenever xi is 1, yi is 1, right?
Yes.
But in that case, sum over I, yi is greater than equals to 1 over 2, right? So majority y1 to yn is also 1, right? Yeah, because the sum is also at least n over 2. Basically, when I flip some zeros to ones, the sum cannot decrease.
Right, right,
Right.
right.
Yeah. So majority is clearly monotone. What about parity? So parity n is the number of uh, parity. Okay, let me write that.
So parity is not monotone. Why? Because
Yeah.
if we flip some of the ones as the zeros, still the parity may remain as odd value.
Right. So parity, this is one if and only if uh, number of ones in x1 to xn is odd, right? So parity 1 is equal to 1, but parity, yeah, so for string 1 comma 0 to the n minus 1, parity is 1, but for string 1, 1 comma 0 to the n minus 2, the parity is 0. But this string is greater than this string, right?
Hmm.
So yeah, what about connect G? C is equal to 1 if and only if G is connected, right? So if G prime is greater than equals to G, G prime contains all edges contained in G. Okay, so my claim is if G prime is greater than G, then G prime also contains all edges contained in G. Let's see how uh, G is given. So we are given input as a vector containing n choose two entries, one for each corresponding edge, right?
Yes.
So when I flip some zeros to ones, all I'm doing is adding some edges, right?
Hmm.
So when G prime is greater than equals to G,
So the graph will still remain connected.
right? Adding edges cannot make the graph disconnected, right?
Yes.
Yeah, so this is also monotone. And what about intersect? To intersect x1 to xn, y1 to yn is equal to 1 if and only if some. Okay, so intersect. Okay, so what happens when I flip some ones? Okay, let me do it like this first. So this happens if and only if or I in 1 to n xi and yi is equal to 1, right?
Yes.
Yeah.
So yeah. So
Okay,
if
so
I if I if I flip some of the zeros at the ones, then I mean the sum of the products will remain greater than one, isn't it? So therefore, this will also be monotonic.
yeah, yeah. So okay, what does intersect x1 to xn, y1 to yn equal to 1 tell us? It tells us that this OR is true, right? So when
Yes.
I then flip some zeros to ones, so okay,
Mhm.
so that tells us there exists at least one I so that this AND is true, right?
Yes.
There is at least one I for which both of these are one. Now, no matter what I do to zeros, these would still stay one. So
Yes.
this AND would still be one. And since there is OR, we do not care, as long as we get one, we do not care what happens to others, right?
Yes.
Yeah, so this is also monotone. Yeah, so A is C and D are monotone, the B is not.
Yes.
Yeah. So we are already over time. So
Your video, your voice, yeah,
oh, okay.
your
Yeah. So I was saying that we are already over time. So if there are no questions, we can meet next time.
yeah, sure.
Yeah.
Thank you so very much. I could
Yeah.
understand the majority of the portion
Yeah.
of today's discussion,
Okay.
and next time I shall be
Yeah.
more prepared. Yeah. Thanks.
Okay.
Thank you. Good night.
Right.
Bye, everyone.
Bye.
Thank you.
Bye.